slide visible? All right. So I'll start the discussions on materials today. So far, you have been going through the lectures of Dr. Mishra, focusing on the basic theories and coding for machine learning as such. And we thought that this is the time we bring in some element of materials into it, because eventually you have to do your projects on the materials. Otherwise, we possibly would have started this after a few more lectures. But anyway, so let me right in the beginning be clear about what I'll be doing here and what I'll not be doing here. Materials is a very broad term, includes all kinds of things. Solid materials and solids can include crystalline solids, amorphous solids, uh, liquids are also material, and so on and so forth. We will focus largely, I think almost exclusively, except maybe one or two lectures at the end, sort of for information. We will focus on crystalline materials. So, this is the kind of materials that you study in your first course on solid state physics or chemistry. Uh, Now, when we say crystalline materials in any real world application, there are no ideal crystals, in the sense that, unless you grow them with lot of care, with, under specific conditions, you don't have single crystals of materials. uh, you have polycrystalline materials, you have grain boundaries. Even in single crystals, you may have defects. You do have defects at finite temperatures. So there is no material which is 100% pure. It can be very, very pure, but it's always less than 100%. So what are the impurities you may have? That, of course, depends on what material you are dealing with and how you have prepared that. But there can be, in general, there can be defects like impurities, there can be vacancies, there can be um, dislocations, etc., etc. Now, all these things have important implications for the properties and behavior of these materials in specific application conditions. And these are real world questions, more important in engineering applications. However, in this course, we will not worry about those things. That can be, of course, an important area of applications of, whatever experimental, theoretical uh, tools we have. But our focus will mostly be on the basic science aspect of it. Assume you have an ideal crystalline material, and then the question is, what can we learn about it, what can we do about it, kind of things that you do in your solid state physics course. All right. So as the title of the course tells you, that we are going to study applications of machine learning to the study of these ideal crystalline materials most of the time. As of today, if I ask what are the major areas in which machine learning is being used for study of such materials, uh, to my understanding, there are four broad areas one can classify, and I'll take you through them. So, the first thing, and this is where we will mostly focus, is predicting material properties using trained machine learning models. What kind of properties are we going to predict? How can we predict? What kind of models do we use? So, these are things that we will discuss in detail. And I'll get to this again in a couple of slides. Then the next question, next area of application of machine learning and AI is searching the material space using generative models. Now, what is this material space I'm talking about? In this specific context, we are talking about inorganic materials. And if you just do a combinatorial sort of estimation, say maybe up to ternary or quaternary materials, you can easily estimate that there would be something in excess of 10 to the 10 to the power of 10 different possible combinations. That's a huge number. And when we are looking for a material for a specific application, what we really have in mind is that the material has to satisfy certain set of properties. And if we are looking for a particular technological application, a, a novel material, it is practically impossible to do an exhaustive search through this space of 10 to the 10 or more materials. It's just out of the question. So there, what this generative AI is doing is that it is helping us to design or generate novel materials which maybe nobody has ever studied before, and start from there. So that is a sort of advanced application of AI and machine learning, and that is something I just gave you as a piece of information. It is advanced for this course, so we will not touch this at all. The other thing is, maybe I will tell you a little bit at some point of time as we go along. But again, if you, some of you can apply this in your project, good. If you don't, that's also fine. Is that, in material simulations, ca- the forces, calculating the forces between atoms, let's say, is very important. I mean, some of you may be familiar with things like molecular dynamics. In this, what you do is you study the dynamics of your system. And the system, typically, in atomistic description, this is, your system is made up of a collection of atoms. And in order to study the dynamics of these atoms, maybe at finite temperature, what you need is basically the forces acting on the atoms. There are several ways you can do this dynamics. I mean, once you have the forces, then doing the dynamics is very simple. You just integrate the Newton's equation of motion. So basically, you treat the atoms as classical objects, and once you have the forces on those, you can integrate the Newton's equation of motion by numerical means. The question is, how do you get the forces? So one way is that there are classical force fields that have been developed in some parametric way. So these are force fields. Given a collection of atoms, you can calculate forces on each of these atoms, which depend on a certain set of parameters. And these parameters have been fit to some known cases, typically through some high level accurate calculations. Now, once you have these parameters, the force field is known to you, and you can just use this to do the dynamics in any configuration of these atoms. The other possibility is what is called ab initio molecular dynamics, in which you solve the quantum problem of the collection of atoms, that is, nuclei and electrons. And once you have solved the problem and you have got the electron density distribution, then it is simple electrostatics. You can calculate the forces on the nuclei and do a dynamics from there. The newest thing in this business is that you train machine learning models on your this quantum or ab initio molecular dynamics that I talked about. Using that data, you train your machine learning model, so that given a new configuration of the atoms, it can give you the forces. So what is the difference? The difference is that the quantum calculations are always more expensive. To do one time step of the dynamics, you need to solve a quantum problem, which takes a substantial amount of time. Whereas if you have trained your model, that training may involve some time, but after the training is done, it's very quick. So essentially, you can do molecular dynamics or any other calculation you may want to do that require forces uh, at the accuracy of a quantum calculation. Quantum calculations are always more accurate because that's the sort of underlying first principles theory that describe everything. Uh, so you can do calculations at the accuracy of a quantum calculation, but at the computational cost of a classical calculation. So these are much, much faster, orders of magnitude faster than a full ab initio dynamics. The last thing is, it's not just in theory and simulations that machine learning is being used. Machine learning is also being used in accelerating the materials characterization processes. And when you study a new material, you synthesize something. Those of you who do experiments, you already know that it's you can just claim that I have synthesized this material. You have to characterize it. You have to establish that it has such and such crystal structure, or these are the elements present in this. And you have to really establish that you have synthesized what you claim. So XRD, the X-ray photoelectron spectroscopy, etc., these are some of the standard techniques that are used for materials characterization. And machine learning is being models are being trained to sort of interpret these data, which accelerates your characterization process, so that you don't have to go one spectrum at a time. So you just have a trained model, feed your spectrum, and immediately you get an answer. So I hope to discuss maybe some of the essential parts of it, how it is being used, and what is the status of it. So these are the four broad application areas, and as I said, I will be focusing mostly on the first topic in this course. So what are the property prediction models? What are we talking about? We can have regression models. You have you have learned about regression models and classification models. So regression models, we can train regression models that predict properties, materials properties, that take continuous values. And some of the simplest quantities you can immediately think about are, for example, formation energy or the band gap. These are real numbers, can take continuous values. You have a magnetic material, a ferromagnetic material, you have saturation magnetization, you have elastic constants, you have thermal conductivity, electrical conductivity, etc., etc. All these things are real numbers that take continuous values. So you can train regression models that will predict these properties. But sometimes we may be interested in other kinds of questions. For example, I may be interested in knowing that given a new material, or if the material exists, of course, I know it's a stable material, but if theoretically you design something and you don't even know whether it is stable or unstable, whether it is energetically expected to even be formed. The first answer I would like to know is that whether it's a stable material energetically or unstable. If it is stable, I would like to know whether it's likely to be magnetic or non-magnetic. If it is magnetic, whether it's a ferromagnetic or antiferromagnetic, etc. So these are obviously all classification tasks. And in these particular cases, the examples that I cited here are these are cases of binary classification. Your problem need not be one of binary classification, but the examples I have given are all binary classification examples. Then the last point is related to what was discussed in the previous lecture, just the last lecture, is unsupervised model clustering. So you have a large number of materials. You go to any materials database. We will discuss material databases. I'll show you examples. Uh, you have all kinds of materials. Now, can I do some unsupervised uh, model so that it clusters similar materials together? Now, what are similar materials? That depends on what I'm interested in. For example, I could say that metals go on one side, non-metals go on the other side, or I may be interested in eventually finding out ferromagnets on one side, antiferromagnets on one side, um, superconductors on the other cluster. Now, all these things done not with a classification model, but uh, unsupervised model where in some cases ideas of graph theory may also be useful or can be applied. Now, not much work has been done along these lines. This broad question falls in the, what can be termed as materials informatics. Bioinformatics is a very advanced sort of discipline. Cheminformatics to an extent. Materials informatics is in its infancy. Not much has happened because of certain complexities in dealing with materials, but that is another area of interest. Okay, now we have trained property prediction models. What can we do? What is the purpose of this? So I give you this background which I discussed in the very first introductory lecture. I'll go over this quickly once more. Uh, so typically, traditionally, how have advanced materials for specific applications been designed, discovered? Through experiments, trial and error experimentation. You use some guess, some intuition, um, and then you come up with a suggestion. You synthesize those materials, you test them, and ultimately see whether that satisfy your requirements or not. Of course, this is very expensive. Any experiment is expensive, time consuming, and uncertain. In recent times, experiments have been refined, and you can now do experiments in what is called high throughput mode. High throughput is sort of an automated way of doing experiments. I won't go into further details of this, but it's still expensive. It cuts down on the time, but it's still experiments are expensive. You have to still do all the experiments, and that uncertainty remains. In order to reduce your time and experimental cost, of course, you do calculations. And the sort of canonical way of doing these calculations, calculating material properties, has been DFT, density functional theory. Some of you may be familiar with this, some of you may not be familiar with this. It's all right, but just understand that density functional theory is a first principles quantum mechanical theory for doing calculations on materials. Not just materials, you can do on any interacting electron system, but this is typically, I mean, this is used for materials as well. So just understand this as a first principles quantum mechanical calculations. It is definitely much cheaper than experiments, but when you have to do calculations on thousands or hundreds of thousands of materials, it still takes a lot of computational resources and time. Just as you have high throughput experiments, you also have high throughput calculations where you can automate calculations on essentially any number of materials. So it's not like you have to prepare inputs for every material separately. You have automated ways of doing it so that calculations are done at the same level of accuracy for all materials in an automated way. So you submit one calculation, and at the end of it, you get results for all your thousands of materials. But still, it takes time. You can't cut down on the basic computational resources, the CPU time, the memory requirement, etc., etc. So the final question is then, can we bypass these calculations altogether? By And here comes the use of machine learning. By leveraging whatever data is available, we can in fact, and that is the sort of message I'll give you throughout this course, that you can bypass these expensive calculations provided you have some data to train your model on. So just look at the figure on the right hand side and keep this picture in your mind. This is one of the areas of application. This is the material screening I was talking about. You have to start with a large number of materials, and you finally want a set of materials which satisfy a certain set of properties, property 1, 2, 3. And what these properties are, we'll see examples as we go along. Now, there may be some that satisfy one but not two. They are filtered out. Then there are more which satisfies, there are few more which satisfy property three but not property two but not property three. So they are filtered out at the next level, and so on. You go along. Finally, you identify a small a much smaller set of properties which satisfy all your requirements. You can either do it through density functional theory, which is expensive, as I said, or this is where you can bring in machine learning. Rather than calculating these properties, if we have property prediction models which predict these properties, then I can do this screening procedure using machine learning models, and that procedure would be orders of magnitude smaller, less expensive computationally than doing full DFT calculation. So that's one area of application we will focus on. You already know what machine learning is. I'll just remind you once again, and confusion matrix is something I will just discuss a little bit. So, what is the idea of machine learning? You have your target variable y, which depends on certain features x1, x2, up to xn, and this y is a function of these x's, except that you do not know what the function is. All you have are some instances, some examples, your training data. So you use your training data to arrive at the best estimate of f. If y takes continuous values, you have a regression model. If y takes categorical values, discrete values, you have a classification model. And you are already familiar with the matrix that are used to, on the left of your screen, you have the matrix that are used to measure the performance of a regression model, the R square value, the correlation between uh, the predicted value and the true value. In this case, predicted values are denoted by y hat, or the mean absolute error, or the mean squared error. Actually, you should be, typically what is reported is the root mean squared error. So you take a square root of that quantity. Uh, Classification models, all the examples I talked about in the materials context are binary classification. So let me tell you the matrix that are used to measure the performance of a binary classification model. So you have two classes, uh, stable or unstable, magnetic or non-magnetic, etc. So one class you can denote as 1, the other as 0. And if a sample is predicted to be in the correct class, that's positive. So let's say in our case, stable is 1 and unstable is 0. If a material is correctly predicted to be stable, you have a true positive instance. If it is predicted to be false, then it is, of course, a false negative. So you can have four possibilities: true positive, false negative, false positive, true positive, based on these numbers. So if you have a certain number of samples in your test set, say capital N, based on the numbers in each of these uh, categories, there are four different quantities that one defines, which together give you an idea about the performance of the model. So one is the overall accuracy. Okay, so let me go to the next slide where I have this thing again. So one is the overall accuracy of the model. So how many out of these n samples are correctly classified? So true positive plus true negative divided by the total number of samples. So that's what is called the overall accuracy. Then precision is true positive divided by true positive plus false positive. So true positive plus false positive is the total number of samples that are classified as positive. But how many of these are actually true? So that is your numerator, true positive. So ratio of these two is called the precision. Recall is true positive divided by true positive plus false negative. Note that anything that is false negative, falsely classified as negative, is actually true. So what recall tells you is that how many of the actual true, actually positive samples are classified as positive by your model. So that is what is called the recall. Now, why do you need? I mean, you might think that accuracy is good enough, but I'll show you this example to sort of convince you that accuracy itself is not a complete measure of the performance of your model. So, what you have on the table on the left is some classification task. It's in a different context, but doesn't matter. So, what you have is 81 samples are correctly. So this is a credit card data default, how many customers were predicted to default, some how many were predicted to not default, and what actually turned out to be the case. So 81 customers were predicted to be defaulters, and they turned out to be defaulters, and so on. So if I, based on these numbers, if I calculate accuracy, I get 97%, which is a very good number. So your model works with accuracy of 97%. You calculate precision, that is uh, how many of the samples, how many of the customers who are put in the positive category are actually in the positive category. So that is 78%. But you look at the quantity recall, which is how many of the positives were actually classified by as positive by the model. So how many who were predicted to be, so look at this number 252. The prediction says that 81 of the customers are likely to default and 252 are not likely to default out of the true defaulters. So 252 members finally defaulted, although the model predicted that they would not default. So if you are using this kind of a model, you will completely lose out these 252 customers who would eventually default, and that shows up in this quantity recall. So therefore you need all of these quantities to have a clear idea of how the model is performing in classifying candidates samples in different categories. And finally, F1 is sort of a combined measure of precision and recall, and you can easily see that it's the inverse of the harmonic mean of these two quantities. So anytime you use a classification, binary classification model, you have to use and understand these properties. Okay, so now I come to the definitions on of some of the materials, quantities, properties that I talked about. First is the formation energy, which is equivalently called the heat of formation in different papers, different contexts. It is basically the energy that is gained when you form a material from its constituents. So you look at the second equation here, the formation energy of a compound of the form ABX3 is total energy of ABX3, a unit ABX3 of the material, minus these mu's are chemical potentials of the constituents in their reference states. Now, this term reference state is very, very important in the definition of formation energy. You have to define what the reference state of each one of the constituents is in order to get a meaningful number for formation energy. So, for example, A, the reference state for the element A could be its solid state. Similarly, for B, whereas X could be in its gaseous state. It all depends on what is the experimental situation. So, if you are, for example, forming ABX3 by a reaction of the solids A and B with some gas X, then that is what you would take. On the other hand, if A also comes from a gaseous state, then the corresponding chemical potential has to be taken as that of the gaseous state of A, and things can differ from one experimental situation to another. So that's the sort of materials or physics or chemistry, whatever you call it, perspective of it. In the context of machine learning applications, what I would like you to be careful about is, if you are taking data from more than one sources, you have to make sure that these definitions are consistent. For example, if in one source, or if for one material A is in the solid state, for a second material which also has A, the reference state is a gaseous state, then you cannot compare these formation energies. So that is something you have to be careful about. All right, so that is one measure of, so this formation energy, as you can easily see, is a measure of stability of the material, energetic stability of the material. Only when the material energy E of ABX3 is less than the sum of the constituent energies, sum of the chemical potentials of the constituents, can you really form it. If that energy is not lower, so anytime the formation energy is positive, that material is just unstable. You cannot form it. Another measure of stability, and it's a different measure of stability. So formation energy measures whether a compound can be synthesized from its constituents in their reference states. But suppose you have a material. Now, it may not break up into its individual constituents, but suppose a ternary material like ABX3 can break up into maybe two binary compounds, some ABX and BX2 or some such thing. So how do you measure such possibilities? So uh, that is sort of estimated by using a quantity which is called the energy from the convex hull. Now, I'm assuming that not all of you are familiar with the idea of a convex hull. So I'll spend a few minutes discussing the idea of a hull and how the energy from the hull is a measure of stability. And this is something you will find useful in many of the applications. So the concepts are mathematical. So what is a hull? Or what is a convex hull? The convex hull. So you have a set. Okay. Convex hull. Suppose you have a set of points to make the discussion simpler. For example, on the right, you have this set of points. Now, convex hull is the smallest convex set that encloses all the points and form a convex polygon. So, a lot of times we are using the term convex. So, first of all, then what is a convex set? Now, that is the next definition. A set P is convex if for any two elements P and Q belonging to P, the segment PQ lies entirely within P. Okay, so you have a set P, you take two elements, any two elements PQ, you consider the line segment joining P and Q. If it lies entirely within P, then it's a convex set, otherwise not. So you have this example on the, now I have got back my pointer. I don't know how, but anyway. So so you have this example, 2D example on the left bottom. This is a convex set. If I take any 2 points within this set, so this is the boundary of the set, and all the points inside it form the set. If I take any 2 points, the line segment joining them will be entirely within this set. So this is a convex set. Whereas if I have something like this, then I can easily see that there are points connecting. If I draw a line connecting them, then this part of the line is outside the set. So this is not a convex set. This is non-convex set. You can have 3D examples of that. This is a convex set, and this object with protruding corners, this is a non-convex set. And now that you understand what a convex set is, Here is a convex hull. The convex hull is the smallest convex set that encloses all the points. So here are the points, and the smallest convex set that encloses all the points is given by this green line or line segments. So this is the convex hull for this set of points in 2D. And you can have more examples in this link. I'll of course share these slides with you. You can play with those. Now, once if you understand this convex hull, it is the smallest convex set. How can we use it in our discussion of stability of materials? So I take the same 2D convex set. Okay, again, I don't know what happened to my pointer. All right. um, so now I draw it. I put these points in some space, and the space is the following. It's a 2D space, and the x-axis is the composition space, so that the extreme left is element A and extreme right of this line is element B. And as you move along this line from A to B, the composition is changing continuously. It is some AX B1 minus X at any point. And the vertical axis is the formation energy. And formation energy is typically given in units of electron volt per atom. So, what are these points then? These points are the formation energies of various binary phases of AB. And of course, we are not interested in materials that have positive formation energies. I just told you. So, the upper part, uh, where formation energy is greater than zero, is of no interest to us. That's an unstable state. We are only interested in points for which the formation energy is less than zero. So, the bottom part, which is sort of unmasked. And now, here what is relevant for us is then those green line segments that define the sort of boundary, the convex hull of this. So that is the convex hull, sometimes called the energy hull, in this binary phase space. So let us take a concrete example on the right. So this is a phase space. This is from one of our own calculations. I'll show you more examples. It's a it's a binary phase space of tantalum and iron. This alloy of tantalum and iron. The extreme left is tantalum, extreme right is iron. And you see different materials, different of different compositions, are designated by points on this plane, and the formation energy is plotted along the vertical axis. So, these green points and the line segments joining these green points basically define the hull, which should be obvious from our discussion of what a hull is. And these red points, these compositions, these are not on the hull. So, given this so basically the hull basically gives you what is the most stable known phase of this binary material at a given composition. So the green circle corresponding to, say, the lowest one, the tantalum Fe2. So that is the one of the most stable materials involving tantalum and Fe2, tantalum and iron. And therefore, if I look at this material Fe12Ta4, this red circle, somewhat above the hull, it may in principle disintegrate to TaFe2 and something else, depends on what is around it, what are the stable phase. And what is taken as a measure of such stability or instability is how far above the convex hull a particular material is. If it is too far above the hull, then it is more likely to disintegrate into other compositions, other materials involving these elements. Of course, you cannot have new elements, but it can disintegrate, it can phase separate. Whereas if it is close to the hull or on the hull, if it is on the hull, means that there are no other more stable materials, that is, material with lower formation energy, that is known. So that has to be a stable material. So the from the hull is a measure of stability with respect to disintegration into other phases. uh, One can define convex hull for ternary phases as well. It's a little more complicated, and I will just give you the basic idea, and maybe there are several ways of calculating things where to put a ternary phase. So you have three elements, right? So this one line going from tantalum to iron is not enough. So in order to represent three elements, you draw a triangle, an equilateral triangle. First of all, three corners represent three elemental phases, in this case A, B and C. So if you move along a particular side of the triangle, suppose I go from the corner A to corner B, that side of the triangle, I am within the binary phase AB. There is no C along that line. So that is similarly, the line BC defines the binary phase BC, and the line AC defines the binary phase AC. When you go inside the triangle, you start having ternary phases. All three, A, B, C, are present. Now, given a particular composition, given a stoichiometry, where should you place this point? I'll just use, maybe there are several ways you can calculate that, and the easiest one to understand is probably the figure on the left. Okay, so A, B, and C are the three elemental phases, and suppose you have a certain point X within the triangle. So you drop perpendiculars from the point X to the three sides of the triangle. You get the points L, M, and N. So suppose this sum of these line segments, the lengths of these line segments, mx, lx, and nx, they add up to 100, let's say. So the fraction mx of it is the fraction of A in the material. The fraction nx of it is the fraction of B in the material, and the fraction Lx is the fraction of C in the material. So I look at one of these line segments, and its length divided by the total length of the sum of these segments gives me the fraction of the element which is on the opposite side. So if I look at Lx, then the fraction Lx of the entire distance gives me the fraction of element C in this. So this way, each point within the triangle define a certain ternary phase, a certain stoichiometry. And then you have to imagine a third axis. So let me go back. Yeah. So then you have to imagine a third axis which is perpendicular to the plane of the triangle, which uh, along which the formation energy or heat of formation is plotted. Again, we are not interested in materials with positive heat of formation. We only look at, or only plot those points for which heat of formation is negative. And then instead of line segments, you connect them through uh, planes or parts of the plane. So each 3 point defines a segment of a plane. So you look at all collection of all these segments of planes, and that is basically the hull in this case. So if a so suppose you have a certain set of known materials, you can construct a hull. Now you generate a new material, you study a new material theoretically, you can calculate its formation energy, and you want to know how stable it is. So you put it on this hull and see how far it is from the hull. If it is too far away from the hull, then it is likely to be unstable. If it is on the hull, then of course it is stable and you should be able to synthesize it, given that you can satisfy certain other conditions. So, what is too far away from the hull? What is on the hull is, of course, obvious. But what is close to the hull? What is too far away from the hull? What are these numbers? There are no hard and fast boundaries, but we go by our experience. And maybe I'll discuss this or mention this later on. Okay, so that is about convex hull. Then another quantity that you can study, which has been studied using machine learning, is band gap. If you have a semiconductor, band gap is a quantity of utmost importance. Uh, Determines where you can use it, for what purposes, and so on and so forth. So, therefore, if you are able to calculate band gaps, that's useful. And on the right you see it's not very clear, unfortunately, but typical band structures of some standard common semiconductors: silicon, germanium, gallium arsenide. Again, band gap, you know we say band gap, but there are different kinds of band gaps, in talking in terms of basic physics. One way to define band gap, and that is sort of the fundamental definition of band gap, is that it is the energy difference between, well, it's the difference between two energy differences. Okay? Let me see if I can highlight this yeah equation. Yeah, sorry, so I deliberately got out of the presentation mode, so that I can highlight certain things, because I'm not able to use my pointer when I'm in the presentation mode. So I'm highlighting this equation. As you can see, the fundamental gap from the definition of physics is a difference between two energy differences. So the first quantity here is the energy difference between a system with n plus 1 electrons and n electrons. And the second one is the last part, this part is the energy difference between a system with n electrons and n minus 1 electrons. So how do you measure this? Okay, and this is actually the quantity that is measured, and this is one of the standard ways of measuring band structure and band gaps of materials, is what is called RPACE, the angled resolved photoemission spectroscopy. So here in photoemissions, photoelectron spectroscopy. So photoelectron spectroscopy is used. So you shine light, you extract an electron out of the valence band maximum, you measure its energy, you can also measure its momentum, you can relate it to the crystal momentum in that direction, if you know which crystallographic direction it is traveling. So basically you can relate it to the k along this plane, and from that you can basically map out these band structures. So again, those of you who may not be familiar with band structures are how your energy changes as you move along certain directions in the Brillouin zone. So this is energy difference between in electron solid and in minus 1 electron solid. How do you reach the n minus 1 electron solid? You simply take out one electron by this photoelectron spectroscopy. How do you go to a 1 plus n electron system? Well, you do what is called the inverse photoelectron spectroscopy. So here, instead of emitting or extracting an electron out of the system, you put one electron in the system, and you can measure the energy gain from that, and from that you can calculate this quantity, and the difference between these two is what is by definition the fundamental gap, and this is what is measured by the angle resolved photoemission spectroscopy. Sometimes one refers to transport gap. This is a completely different quantity. So at zero temperature, as you know, all the valence band is completely occupied. The conduction band is completely empty. So in a semiconductor, there is no conduction. But then when you are at a finite temperature, electrons get excited to the conduction band. So you have holes in the valence band, electrons in the conduction band, and you see some conduction, and you can relate the conductivity, electrical conductivity at temperature T. So that goes like this because it's an activated process. And so you can see that log of sigma would go as something like this. So basically, then you can measure sigma as a function of t, plot it as a function of 1 over t, and from that extract this quantity, this gap. And I have deliberately put this E transport. Okay. And this gap are two different quantities. They need not turn out to be the same at all. This is a difference. This involves changing number of electrons in the system. This does not involve changing number of electrons in the system. This just involves excitations of one electron from the valence band to the conduction band. Then there are optical band gaps. I'm not getting into the detail of that. So these are experimental band gaps. But then you can, of course, you have data sets where gap has been calculated by DFT, density functional theory, under various standard approximations. And none of these approximations get the band gap quite right. You can build in many body effects. So these do not build in many body effects very well. They do not describe electron electron interactions or even excitonic effect very well, this standard DFT methods. But there is something called GW, Gutzweiler approximation, which solves something called Bethe-Salpeter equation. We'll not get into any of these technicalities. But what I'm trying to tell you is that there are advanced methods which take into account electron hole binding as excitations and give you a different band gap, which will be different from the band gap you calculate through standard DFT. Now, I'm telling you all of these because some of you would be doing projects on things related to this. The point I'm trying to drive home here is that you cannot, you should not mix different quantities. For example, you should never, while training your model, you should never mix GW gaps. You should never mix GW gaps with LDA gaps, or never mix LDA gaps with GGA gaps. Or there are GGAs are also of many types. So whatever gap you use, whatever quantity you use, consistency of your data is absolutely important. So if you're training your model on this quantity transport gap, assuming you have enough data to train your model, then you have to consistently use this transport gap. You cannot mix in your training data transport gap and DFT gap. Okay, so that is the point I'm trying to drive home here. Okay, all right. Uh, that's the message. Don't mix data. This is simpler. Magnetization, ferromagnets. You can calculate it through DFT. You probably have measurements. You may have experimental data set. So you have to be just careful about the units you use. But anyway, this is probably a simpler quantity to deal with as far as consistency of data is concerned. Okay, now in order to train any model, any machine learning model, we need data. You already know that. Um, where do we get data? Turns out that even say 4 or 5 years ago, having large volume of materials data to train machine learning models was very difficult. But things have dramatically changed thanks to the materials genome initiative and all the activities it spawned. So we will actually go through some of the big databases, and for a few, maybe 2 or 3, I'll show you how to download data. The others you can explore on your own. I some of you, and here let me just talk about two of the very well known experimental databases. The biggest one and the most trusted one is, of course, ICSD, Inorganic Crystal Structure Database, but this requires a subscription. If your institute has a subscription, you can access it. There is an open database, crystallography open database. Maybe I'll show you these next time. As I said, we'll get familiar with a few data sets. So the point is that there are a large number of DFT generated databases have come up. So I'll spend most of the time making you familiar with those, telling you how to download data from these databases. Let me see if there are questions. We are almost. So the question is, yeah, you showed the hull for two phases A and B, then points other than the points connected by segment are not considered in the hull. The points not connected by the segments are not on the hull, they are above the hull. So the hull is composed of these line segments. This is the hull for this phase space. These points are above the hull, and from here to here this vertical distance in energy, so this is your energy axis, the vertical axis is the energy axis. So the distance of this point from this, wherever, if you draw a line parallel to the energy axis, then wherever it touches, this distance is the distance of this phase Fe12Ta4 from the hull. And if this distance is far, so you see there are two Fe. Let me try to enlarge this. Yeah. So you see there are two Fe12Ta4 phases here, which means that they would have different structures, different crystal structures. One is this much above the hull, the other is this much above the hull. So obviously this is more unstable than this. So if this distance is too far, then it is unlikely that you will be able to see that or synthesize that phase. If it is close to the hull, like this one is pretty close to the hull, it may be possible to synthesize that. And this is an intuition, this is a sort of knowledge you develop over time. Uh, Today you won't be able to tell which one may be synthesizable, which one not, but you know, with experience, with knowledge, you have some idea. Okay, so I think we have sort of exhausted today's time. So if there are any further questions, I would address those. Otherwise, I will take up the discussion from here in the next class. Okay. Since there are no more questions, so what I'll do is I'll share these slides. I'll send this. You will get this on the same course page, and you can go through this. Mixed transport gap and band gap. No, 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 no. See, everything is loosely clubbed as band gap. Okay, but then you have to ask the question: how is this band gap obtained? If it is an experimental number, what is the experiment that was done to obtain this number? If it is photo emission and inverse photo emission, it means something. If it is obtained through transport, it means completely different thing. If it is measured from optical measurements, it means yet another thing. So what I'm telling you is each one of these things means a different thing. When you train a model, you have to consistently train it on one kind of data. You cannot train a model in which you have, for some materials you have the r pace inverse r pace gap, for some other materials you have the transport gap. That will be completely meaningless. That's what I'm saying. All right. So it seems there are no more questions. So we'll take it up from here next time. So bye.